Hello, friends. This is Joanna. I'm not a maths person, and I'm going to walk you through something that blew my mind this Sunday afternoon, and I feel like I just have to share stuff that I'm learning. So I am watching I started this engineering mathematics lecture series because I'm interested in maths, and I wanted to know what uh, ordinary differential equations are used for. And I'm also a software developer, uh, pretty generic software developer. And I wasn't expecting to see models in the first lecture. So I wanted to talk about what is a model? And this was a really nice example that Steve Brunton, the lecturer, gave. So here, he created a matrix and started doing matrix multiplication, and I just had to remind myself of what that stuff is. So the example that he gave is the weather in Seattle, which was also really cute. So he had this state diagram, which for software developers is really, and anybody maybe, it's really easy to understand. So the weather is either raining, cloudy, or nice in Seattle. And then the chance of it being rainy, nice, or cloudy the next day really depends, on the probabilities. So he gave some probabilities of, if it's raining in Seattle, there's a 50% chance that it'll rain again. There's a 25% chance that it will be a nice day, and 25% chance it'll be cloudy the next day. If it's a nice day, there is 0% chance that it'll be a nice day tomorrow. 50% rainy, cloudy, etc. And then for cloudy, something like this, right? So this kind of state diagram is really familiar to us, and we can use it to model the weather. We can just say, if it's rainy today, there's, tomorrow the chance is 50%. But if we were going to say, what about, 2 days' time or in a week's time? So the chance for tomorrow, say it's raining today, and tomorrow there's a 50% chance. Like that's super obvious. But what about, the day after, since it's plus 1 day, plus 2 days? It's really tempting to just say, well, it's 50% chance of 50, so it'd be like, 0.25 chance of rain. But that's not correct, because there are other ways that it could have become a rainy day. So, maybe tomorrow it doesn't rain, maybe it was a nice day, and then there's actually a 50% chance from that nice day. So it's, there was a 0.5 chance of it being rainy, a 0.25% chance of it being nice tomorrow, and then the day after, it's going to be more chance of it becoming rainy, and then tomorrow 0.25% chance of cloudy, and to get back to rainy 0.25. So if you add them up, do you want to watch me do arithmetic? It's really painful for everybody. What is that? 0.25. 0.125. And this one is a quarter of a quarter, which is also, I kind of know these have got to add up to, no, I don't. This is really painful, but that's okay. This is life. well, I know 25 times 25 is 625, so it's probably that, right? And you add those numbers up and you get a probability for it being rainy in day 2. So there's I could program this in code. I could have like if statements checking if the previous state was this, then do that, and kind of add all the probabilities together and just create a little function. And this function I could just iterate over the number of days that I wanted. What's it called? A forecast for, but there's actually a better way, and I'm just gonna show you that. Okay, so here we've got a matrix that can keep track of all of the probabilistic transitions. So I've called it like R with an I to mean like the input or the starts off as rain, and then what's the probability of it raining the next day. So like R output. I'm not super happy with this I and O, but I kind of wanted, this is the starting state and kind of next state. Maybe a better notation, I think, is like N and N plus 1. So like N is the current day or the current position from which you're computing, and then N plus 1 is the next state. So these are all the ways to get to the rain state. So if you're in a rain state, you've got a 50% chance to stay in a rain state. If you were in a nice state, 50% chance to get to a rain state. If you're a cloudy state, 25% chance. And if you're a rain state, likewise, 25% chance that you'll end up in a nice weather state. So this kind of maps out, 3 by 3, all of the possible transitions. And then he says you can just do matrix multiplication. So if your starting point is these probabilities, so like today it's raining, and you can just multiply this by this to get the next state. So matrix multiplication, I had to remind myself what that is. So you call like this matrix A, and you call this vector matrix thing X, and then the next X, so like the X for tomorrow equals A times the X of today. That was X0, for example. So how does matrix multiplication work again? Matrix multiplication, I think they just made it up, right? Like they made up that it was, this is a new kind of mathematical entity, and multiplication of it works like this. If you think of them as vectors, so like these are kind of some horizontal vectors going on here, and this one's like a vertical vector here. Then, as with classical multiplication, you take this thing and you combine it with each of these in turn. So, if I called this like U, V, W, and this one was like Y, then the resultant matrix is going to be, it's like actually the dot product of U and Y, the dot product of V and Y, and the dot product of W and Y. And then that's like the new result, which is a single vector, as this one was. If I had more vectors in here, so I had just for illustrating matrix multiplication again, something like that. And that would be a second one. So I did the multiplication of this against these three. I have to do the multiplication now of that against those three, and then that can be in the second column. So it'd be like U, V, W, and this was like, say, Z. And that would give us, yeah, a 3/2 result. And dot product is just matching up. So for this one, I multiply these two plus multiplication of these two plus multiplication of these two, and that's the result. So if we go back to the working example of starting point of probabilities, I just get 0.5 plus something times 0 plus something times 0, 0, 0.25 plus something times 0, something times 0, and 0.25 something to 0 to 0. And that's like the really basic kind of result of like just going to the next state, like iterating once through this model. I think the reason I kind of asked myself, how does this matrix multiplication work out in this case? So because I started off in the rain state, it's saying that, okay, you are in the rain state, so your probability of getting to rain in the next state is this. Put that here. And because I wasn't in any other states, they don't contribute. So I've got the answer of the probability of being in the rain state. Then I go and find out what's the probability that I'm going to end up in the nice state. Well, I'm in a rainy state, so I get to add that probability, and I'm not in any other states, so they don't count. And then, yeah, what's the probability given my starting point that I'm going to be in the cloudy state next? Well, I'm in the rainy state, so I know it's 0.25, but I'm not in the other states, so I don't count them. So it just kind of just works, just matches up really nicely. And the reason that doing it this way is better than just having an if statement in your own little function is that you can like easily kind of iterate over this now, because this is generically speaking as, yeah, say we, to get to the next x, it was, sorry, it was the starting x. To get to the next x, it was this big matrix, which they call a matrix multiplication of the starting vector. I was asking myself why they call matrices A. I think they just had to distinguish them from other things, from vectors or from normal numbers, and so they use capital letters, and they just start at the beginning of the alphabet. So if I wanted to get like, x, the second x, I would just multiply, because this is a generic matrix, I take my new starting point is x1, and I could keep going, x2, etc. But interestingly, if I look at this one, x2 equals a times x1, which is a times a of x0, and this one is equal to x2 is like a times x1, sorry, a times x1 times a of x0. So what's actually happening here is that like you're just multiplying out this matrix, and then you get this general formula that whichever n I want, I just have to multiply the matrix by itself from the starting point. And that's a very strange and interesting thing. And I'm going to show you in code. Okay, so here I am in my Python terminal, and I'm going to use this numpy thing. Sorry. Oh, let's try that again. Okay, so I'm going to do a basic matrix multiplication. So I'll say A is NP array 0.5. Oops, 0.25. 250. And then X is my starting point vector, which says that I'm raining today with a probability of 1, and I'm not in any of the other states. So now if I want to find out what is the probability of the rain of the weather tomorrow, I just do this matrix multiplication of A and X. And that's what we got before by hand. But now if I wanted to say in 10 days time, I can do I'm just kind of repeating it over and over again. That's not what I expect. That's because range equals what happened there? 0.5, 0.25. Hang on a sec. I found it. My A array is wrong. So if I set X back to the starting point, there's all this stuff. Okay, and then that's the probability after 10 iterations. And if I iterate another 90 times to be 100 all up, that's what the probabilities are looking like. It's really interesting, right? Because you kind of, where did this 0.4 come from? So if I had another starting point, so say, X was the probability, like, actually it's a nice day today. And if I just did one iteration, that's the probability that's going to be nice tomorrow, which is, as we expect, not going to be nice tomorrow. But then if I iterate over it, 10 times. That's what the probability is looking like, which looks kind of familiar if I iterate a bit more. Now it's the same. So mysteriously, doesn't matter where I start, the probabilities of like the 100th day in the future, of course, always gonna kind of be the same. It's kind of really interesting. And if we instead did this with this matrix kind of multiplication thing, so we know that the multiplication, we could just be multiplying the A matrix by itself. So I'm going to make just a matrix in this library. Whoops. So that I can do stuff like this. So A, that's the basic matrix, but if I square it, the probabilities start changing. Yeah, and then if I go to 100 iterations of it, that's a really interesting result, right? And it actually kind of converges there a bit quicker, sorry, a bit quicker. So that's kind of the next mystery, is what's happening when we multiply these matrices by itself, that it's converging to this set of numbers. And then as you can see, like if I multiply that with a 1, 0, 0 vector, I'll get this column. If I multiply it with a 0, 1, 0 vector, I get that column, 0, 0, 1, that column, and that's like the 3 different days. So I get exactly the same result for all of my starting outcomes. That's fascinating. The other thing is like the person who introduced matrices into maths in the mid 1800s, Cayley, he talked about, he defined matrix multiplication, right? Which is why I said it's just a definition of they did these operations and saw that it could work this way with some nice properties. I always say that has to have some nice properties. But the other word he called it, apart from multiplication, is compounding. And this kind of really has an intuition for me. It's also like compound interest. You know, when you say that you've got 5% interest times the principal, and I'll borrow 100,000. In the first year, it's gonna, the loan's going to be that much. But as I go over time, it's going to be more and more times every year that I'm adding this 5% interest. So instead of like doing it with the principal each time, I could do it up front and just say, well, if I do it over 20 years, that's the kind of total factor of my principal that I'm going to have. So it's this like kind of compounding the thing out the front, which is kind of like this, how it is with this matrix equation. And yeah, I guess this way of modeling it, apparently it's called a probability transition Markov model. If you didn't know that and you created this if statement code model, it's just a shame, because like this is a much more powerful, elegant way of solving things and a common way of solving these kind of problems. So definitely going to look into what a probabilistic transition Markov thing is. And I just wanted to end on kind of like what is a model, because I don't code a lot of models, and like we talk about machine learning and having these models that we train up and then that we tune and we deploy, and then what is a model actually? What is it? So I think like a model is just a black box that you ask a question to. So usually it's a question about prediction or a classification. So, how much is my house going to be worth in 5 years' time? There is like a program, some kind of algorithm, some kind of technique, some kind of like, it's usually got a mathematical basis to it, like this weather forecast here, that's just gonna like be able to answer that question either like straight away or by iterating, a few times over things. That's, yeah, I think that's the basic understanding of model, but a lot of us like just kind of throw this word around a lot. But actually, like, maths was always about having models, mathematical models for things. Yeah, so this is like really exciting. He also mentioned that this equation is like a kind of differential equation, which really perplexes me. He says it's actually a difference equation. And so I'm hoping that I'll understand that one day. And the other nice thing about like this matrix is there's some like constraints in here actually. So the probabilities like of going to the next state cannot exceed 1 in all of these columns. And then in the result you get back, like, we'll never get a result that has the, that also adds to more than 1. So somehow in this matrix multiplication technique, like, that constraint will be, kept. And if you were doing like this big if statement thing, it would be kind of maybe very easy or much harder to kind of check that these constraints are kept. Yeah, that was my mind blown dump for Sunday afternoon. The first time I'm trying to record something. I hope I'll get better at this. Give me comments so I would love to hear what you're interested in and what you think as well. Bye.